Hello, everyone. Welcome to the ILTA Physics online problem-solving lecture. Today, the problems we're going to solve together are all about Newton's third law. Newton's third law is widely known as the action-reaction pair. In other words, you can think of it as the give and take law of the natural world. For example, let's look at the movement of a swimmer pushing off a wall in the water, as shown in the picture below. When the swimmer's feet apply a force to the wall in the rightward direction, the wall pushes the swimmer back to the left with an equal amount of force in the opposite direction. One thing to be careful about here is that even though the direction the swimmer actually applies force is to the right, the result is that the swimmer's body, meaning the direction of the object's motion, moves to the left. I'll explain this in more detail using signs and a coordinate system during our problem-solving session. Just like the old English proverb about life's truths, Newton's third law describes a law of nature where what you do comes back to you, a kind of cause and effect. The only difference from our lives is that in physics, the reaction is absolutely instant. So let's start by briefly summarizing Newton's third law once more. The law of action and reaction describes the relationship of forces exchanged between the agent that applies the force and the object that receives it. Basically, it says that if one object exerts a force on another object, a force of equal magnitude and opposite direction is exerted back on the original object. We can express this with the following formula. This means the force object exerts on B is equal in magnitude and opposite in direction to the force object B exerts on A. Let's look at a very common example. Hitting a nail into a wall with a hammer. When the hammer is the agent applying the force, and the nail is the object receiving it, the force the hammer exerts on the nail is toward the right, shown by the red arrow. At the same time, the nail also pushes the hammer back to the left, shown by the blue arrow. In this case, the nail becomes the agent and the hammer becomes the object. Common sense tells us that the hammer is hitting the nail, but physically speaking, the nail is also hitting the hammer with the exact same amount of force. There is something you need to be very careful about here. Sometimes people make the mistake of drawing the forces acting on two different objects in a single free body diagram and acting as if they cancel each other out. However, a diagram where the agent and object are not clearly defined has no physical meaning. If you don't have a solid understanding of Newton's third law, the action-reaction law, I recommend watching my theory lecture first before coming back to these problems. Now let's solve some basic types of problems together. Problem 45 is a basic type for understanding the law of action and reaction through a free body diagram. In this problem, we need to draw a free body diagram for the forces acting on a car that is skidding on the road because the brakes were applied to bring it to a stop. First, let's think about the forces acting in the vertical direction. The car receives a downward force called gravity toward the center of the earth, and the road exerts an upward normal force of the same magnitude on the car. Because these two forces are in equilibrium, the car does not move vertically. Now let's think about the forces in the horizontal direction. The car's tires apply a force to the road in the leftward direction to move forward. At the same time, a frictional force acts on the car as the road pushes it to the right. The directions of the horizontal forces are where it gets confusing. If we zoom in on the tire rotates clockwise and pushes the road to the left. However, due to the reaction force, which is friction, the car ends up moving to the right. Please be careful, as the direction of force and the direction of motion can change depending on what you consider the agent and what you consider the object. Problem 46 involves a squid moving forward as a reaction to squirting out water. This type of action-reaction motion is also called explosion or ejection motion. In the problem, a squid with a mass of 1.5 kilograms moves to the left with an acceleration of 20 meters per second squared while pulling out 0.15 kilograms of water. The question asks for the magnitude of the force acting on each and the acceleration of the squirted water. Let's imagine the squid is pulling water and moving to the left, as shown in the picture below. Representing this as a free body diagram would look like this. I want you to look closely at the direction of the forces appearing as action and reaction. First, we use Newton's second law for the motion of the squid. The product of the squid's mass and the squid's acceleration is the force the squid applied to the water, which calculates to -30 newtons. Please note that the acceleration is negative because the squid is moving in the negative x direction according to our coordinate system. According to Newton's third law, this becomes the force the water pushes the squid with, in the same magnitude but opposite direction, which is 30 newtons. Now, the acceleration of the water is the applied force divided by the mass of the water, which results in an acceleration of 200 meters per second squared. We can see that the water is being pushed away with a very high acceleration. Today, we solved some fundamental problems regarding the law of action and reaction. The calculations themselves aren't difficult, but it's important to accurately understand the physical meaning and the relationship between the agent and the object. That's it for today's lecture. You all did a great job. See you next time.